Okay, so we are muted.
But that's like just as good as when you have like slides. You can annotate. So
Well, I used, in the old days when there were no tablets. Where is my chair? Sorry, trying to get here. I didn't share my screen. I'm not going to mention any names, but there were some faculties that are probably about to retire or about retiring right now. And I took classes with them, and one of them was 4502 and optics as well. So, one of the things we realized quickly is that, like, some professors would just come over and start filling out all these three boards in here, equations, right? And then, having taken a few courses with him, we realized that we are about to go through 150 equations of pain, but only really the last three really matter. So the rest of it is it's browsing through, right? And when you are writing, you can explain. You can do it all, right? So it's difficult. So a lot of the stuff that I'm trying to do here is not mathematically, but it's rather the understanding. So trying to grasp the concepts, and it's what I'm probably going to go even slower. This is a very important chapter, and it will be a question from this as well. So what is it that we're trying to do here, right? So we have a transmitter, we have a channel, we have a receiver. But the transmitter and receiver suffers from the disadvantage of technologies, right? So how do we actually exploit this? And it is a big problem. I mean, so if you look at it's not only a technological problem, it's also an engineering problem. And remember, engineering is about making money. It's about trying to make a cost-effective solution. So I would always want to deal with the lowest possible substrate or technology node that I possibly can. Why? Because I explained to you, if you go from just to give you some references, you do a design in a points in a 65 nanometer technology, that's about $250,000 US per fab cycle. You go through a 45 nanometer SOI, we're looking more about close to $1 million, maybe 900,000 US when it's all said and done. And you go into a 3 nanometer process from Siena, is $10 million or more. That's a lot of money, right? So you don't want to. So if I can squeeze performance out of technologies to be able to meet the bandwidth requirements of all these high-speed electronic systems, then that's a big plus, right? So that's what we're trying to do here. So gate bandwidth trade-offs, understanding that, how can we squeeze, just when the circuit is, or when the system is about to fail and starts to drop because of poles and zeros and all the other stuff, can we give it one last kick, and we do that through inductive and heating and all the other stuff? Neutralization. So we'll sort of see it high level without really getting so much into it. But we do need to understand from here, gain bandwidth product, this curve in the middle is extremely important. So have a look at this, right? If we were to plot the gain as a function of bandwidth, point in which the gain becomes 1, the bandwidth is maximized. That point in frequency, we call it the FT, or the transit frequency, and it's a performance indicator, a figure of merit that allows you to benchmark how good is one process versus the other. But it is an intrinsic behavior. So we need to, what does intrinsic mean again? It's internally the physics of the process that you're dealing with, right? It has a given doping level, and that generates the profile with respect to its ability to modulate the input signal, i.e. the transconductance, but it's all internal. It's intrinsic to the device. You cannot do anything. What we can do is we can actually control the geometries around it. We can shape the way that the source and drains are defined, how the gate comes in. And the moment we do that, then we start to introduce our own personal touch into it. And that now becomes a problem that has the intrinsic versus the extrinsic, which again is a problem for Fmax, right? FT versus Fmax. So, so we looked at some of this. We'll talk about a distributed amplification later. I think where we left off last time was we talked about channel inversion, which will be covered in equalization later. remember I talked about, so this is a kind of a very neat, simple way of looking at this thing, but this circuit here has actually changed the way we do oscillators. And the interesting thing is that it was actually, I wouldn't say invented, but the first time that it actually came about in a research publication was actually a fellow from Raufoss. Okay. So he basically did a cross-couple pair that generated negative resistance. This paper, it came probably in the 1990s, and the student at that time who did it was presented at one of the most prestigious conferences in San Francisco, which is called the International Solid State Circuits Conference, and it's a venue where 15,000 electrical engineers and researchers from around the world showcase their best every year. So when you go with something like this, obviously you're going to be grabbed, right? So he was grabbed, instantaneous millionaire over in California, and the rest is history, right? So what this is all about, again, is the concept that you have a resonator, and I've done this in the top right corner, which is formed by an inductor, a capacitor, but it also has losses. And those losses are as a function of the series loss. So you think about a transmission line, you got the L, you got the R, you got the C, and then you got the G, right? Well, maybe that's fine. But in the actual series resistance, or R, is a function of the metallic losses in the circuit, and we also said that the G is a function of the dielectric losses. So combination of all of those. And then you could say, well, why is it that you have a series component and a shunt component, and you're basically all lumping it into a parallel component? Because it is possible, and I will show you, it is possible to actually do series Jesus. Okay, right here. So we are actually going to look at images, and yeah, we're gonna take this one. Okay, I'll just add this to the notes. So if you have a series resistance or a series impedance, it's possible to convert it. I'll just save it to my device here. And we go back. Discard. I think I saved it already. It's possible to convert it into it by using the following approximation, which is shown here. Okay, so if I go to my notes, how am I going to do this? Maybe here, and I add, insert an image, and I go here, done. Okay, and insert an image. Where did the other one go? Browse camera. Is it this one here? Nope. Okay, let's just cancel this. So effectively what we had is I'll just throw it here. Okay, so this is XP and RP and RS and XS, right? So it is possible to convert a series resistance into its equivalent power resistance by knowing what the Q of the system is. But the Q is basically equal to RP over XP or XS over RS. So if I know the Q, I can then convert RS. Sorry, is something missing here. So RS equal, and RS will be equal to RP divided by Q squared plus 1, and XS will be equal to XP Q squared divided by Q squared plus 1. So you can do the conversion. So in the oscillator that I was showing you, you can easily take the resistance from the metal, which is the series resistance you see here, and the conductance, which is resistance by definition, and you can combine it together to actually form these plus R and this again. But one of the neat things about it, and I said in class, is that we can actually generate negative resistance. And why am I bothering with this? Because along the way, along the side of channel inversion and losses in systems like high-speed systems, we will encounter circuits that will actually benefit from having negative resistance. How do you analyze it? Just a very simple explanation here. You have a cross-coupled device. So, and then you know that the voltages are equal by opposite direction because of the fact that you have symmetry. So if you take the voltage across the device M1, I'm just going to label this M1. You have a VGS1, and then you have a VGS2, right? So you can rewrite these by a transconductor in which you have the current flowing through it as GMVG1 and the current flowing on the other side of GMVG2. And how do you do input impedance, which is really what we're trying to look at is what is the impedance looking into these two nodes as well, right? So how do you find that? Well, you have a Vx and Ix, or Vtest and Itest. And if you do that, you basically equate that the VG1 is equal to VG2, but GMVG2 by definition, if you were to call the, is actually equal to the opposite of GMVG1, so you have a negative factor there. And by definition, then we actually say that V2 is equal to V1 because of the sign of the voltage that we're, or how the polarity on how we're measuring it as well. So V2 is equal to negative V1, Ix is equal to GMV2, but V2 is equal to negative V1. So if you were just to combine those together, you have Vx over Ix, and Vx is equal to 2V1, and Ix is equal to negative GMV1. You cancel the V1s, and you figure out that the actual resistance, which is Vx over Rx, or Zin, is actually equal to negative 2 over Gm. That's actually a negative value by definition, and can be controlled by the transconductance of the device, which is controlled by the current or controlled by the W over L. Pretty cool. So you can do that, right? So you got a circuit that has negative resistance, i.e. loss. You can cancel it out by actually introducing a negative value as well. We talk about feedback theory. Do we know what we're doing here? One of the questions in the assignment talks about this, right? Basic equation is shown right here. You have the starting transfer function, H of S equal to A of S plus 1 of A of S and S of S. But if you were to then add or look at the DC function of it, which is A of S equal to A naught over 1 plus S divided by P naught, where P naught is the dominant pole of the system, and F of S, the feedback factor, making equal to F naught. If you rewrite that into the H of S equation, you'll see that, yes, you have actually improved the pole relation, which is the denominator. So this section here tells me that the actual pole has been moved to the right, but at the expense of a reduction in gain. It's kind of the gain bandwidth product in a way, right? So negative feedback reduces the gain, increases the bandwidth. Positive feedback, that's the opposite. Different ways of doing it here. You can have resistive feedback, either in series or shunt, or you can have reactive series feedback, either in series or shunt as well. And this reactive shunt feedback would actually be used later to actually do things like so we'll look at that in this lecture today. And one of the questions in the assignment actually asks you about a very simple analysis of that. So I'm not going to give you the answer, but I'll get you started and we'll go from there. We also talk about impedance matching. Okay, what is the purpose of impedance matching? Have you guys ever, is that covered in 2507, 3509? How many of you don't know what impedance matching is and why do we need it?
I just know based on what you explained. I just know based off what you explained. Based off what you explained. Like earlier in the course, we talked about impedance matching. Okay, so you can not have a question, right? We don't have this.
That's exactly it. And the purpose of it is to make sure that you have maximum power transfer. That all that you can put in goes in and doesn't come back to you. Reflections are not good unless you purposely are trying to do that. And sometimes we do. But in general, what we want is we want to get as much into it as possible. So when you have discontinuity, discontinuity is equal to one impedance is another impedance and are not the same. The moment that happens, you have a discontinuity. That discontinuity will yield to reflections. And those reflections are inevitable, but they can be controlled. So purpose of a matching circuit is what? You got left, you got right, and you put an impedance matching in the middle. What is the main purpose of it? High level. Yes, but what are we doing to the two of them? How are we doing this? We're basically going, so you have this impedance matching circuit on the left, in the middle, and then you go to the guy on the left and you say, hey, what do you need? I would like to see this impedance to be able to give you maximum power transfer. And then you go to the guy on the right and you say, what do you need?
This is like after analyzing like parasitic element.
Well, you look at the two competing impedance values that you have, right? And what it does, it transforms it. So it makes, so if you have a two-port device and an interstate matching, what it's really doing is actually making, so this is confusing because there's more than one here, but let me just introduce a page here. We'll go through that. So page after, yes, okay. So you have a DUT, I'm gonna do one side, and you have effectively your, I don't know, I'm gonna call it your port one. And you have to actually do matching. And this is basically your input matching, right? So the actual DUT has an impedance, DUT, okay? And we're trying to figure out what we have to present. And then the actual port, if I do this on this side as well, actually likes to see a Z port 1, right? So by definition, most ports are 50 ohms. So let's say the ZP1 is equal to 50 ohms. And let's say ZDUT is actually equal to some value, which is R plus JX, right? So what we're trying to do here is that the input matching is trying to make the most out of the whole situation by making the DUT feel like it's as the ultimate and absolute best possible impedance to for maximum power transfer. And similarly, port 1 also sees what it wants to see. So DUT sees what it wants, port 1 sees what it wants, and it's basically a transformation ratio. We're trying to transform the impedance of the DUT into what we want to see on port 1. So I want, from this point of view, what would I want to see? Based on what you know here, 50 ohms, right? Because 2501, I believe that's when you give the maximum power transfer is achieved when the two impedances have the same value. Right? So we'll write it down. So maximum power transfer when you have a source and you have a load and RS is equal to RL. And the interesting thing is I said maximum power transfer. I didn't say maximum voltage transfer or maximum current transfer. Those are opposite, right? If that's what I was asking you, what do you think RL to be will compare to RS to have the maximum voltage transfer? Well, RS is fixed, so we need to make RL as large as possible, right? This is basically just a voltage divider. And if you're trying to do, so effectively for maximum power transfer, RS is equal to RL. And we proved that in 2501, we're not going to do it. Now, so we need to make this part here look like you're looking into 50 ohms. And on the other side, we need to make ZIP equal to what? Well, 50 ohms is typically what's sending.
Right. So you can also minimize the increase there.
Well, there's one value that is going to, without a doubt, be able to perfectly match 50 ohms to R plus JX. And it's like creating a transformation matrix cell which is going to transform 50 ohms to the conjugate match of the input impedance. So if we have R plus JX, this input impedance will have to be R minus JX. Right? That's basically the rule here. But what I was trying to get at is that the purpose of the input or output matching network is to convert 50 ohms to R minus JX and convert R plus JX to 50 ohms. That's what it does. It goes both ways. That's effectively what we do. So in a typical network system, you have a source, PS, with a source impedance, RS, trying to send a signal down to an RL or a load. And a typical, this is actually a very simple network. It would actually be composed of multiple stages. And two-port devices simply means that is something that has an input. And I know I've shown you as two ports here, but really the bottom one is the ground return. So you have an input and you have an output. Similarly, you have an input and you have an output, right? And a two-port device can be what? What is a two-port device? Let me give you some examples. Resistor, capacitor, inductor, what else? A diode, yeah, sure. What about a transistor? No, not even. Let's say I don't connect to like a diode. So if I have a transistor, let's go with bipolar because you guys are probably more familiar to that. So you got a base, you got a collector, and you have an emitter. That's 3 ports. But if I want to build or amplify anything out of that, what do I typically do? I go with what you guys learned in 2507, which is a common emitter, common collector, or a common base. What does common means? No, it's perfect. You said it. It's basically either DC or AC grounding something, right? So in the case of the common emitter, what do? I take the same device and I effectively just ground the emitter. That's why it's called common emitter, right? We're basically AC or DC shorting the emitter, and then you still have the base and you have the collector. Hey, guess what? That's your 2 port, right? In the case of the common collector, you take the same device and you short the collector. You have the base, and then somewhere in here you have the emitter. That's the common collector or source or emitter follower. And then in the common base, that's a really interesting one too. So in the common base, you got your base, you got your emitter, and you got your collector. And the base cannot necessarily be shorted because if you short the base, what happens? This is an NPN device. Work, right? So you can't really short it. So you still have a biasing network here because you need to bias that base, right? Because VBE has to be positive for an NPN device to conduct. But I already have 2 ports committed. Sorry, 3. So I have 2 ports. I cannot afford to have another port. So how do I do it? How do we do it in 2507? How can I generate a common base? Remember, I say DC or AC. We were lucky enough that in the common collector, I could DC shorted VBE. And is VBE a short? Not DC, but what about AC? Yes. Okay, so it is a short, AC short. In the case of the emitter, we can just put it down to ground and it's DC and AC short both. And in the case of this one, we cannot really satisfy it in the DC, but I can come back and actually add a very large capacitor. And I'm going to call it C large. Because a capacitor at DC behaves like what? No, DC. Open, right? Yeah. And at AC, sorry, I heard the opposite. It's a short. So AC wise, effectively short that node, and now 2-port device. So that's what it means by a 2-port. And it can also be a whole combination of other circuits that like couplers. It could be anything that can be generated into a two-port device. And it's possible that we can do things like converting a three-port into a two-port, a four-port into a two-port. It's all sorts of things that we can do. So that could be anything. But the bottom line is you have input matching, some kind of a device. Then you have a secondary device, and you have the output matching. It is customary and simple in many cases just to actually input match the first stage and output match the last stage, which is just the input to it and the output to it. But what happens is these two devices themselves would actually see a very large discontinuity. So we introduce something in the middle called an interstate matching. Not very often you see this in the 3509s or the 4505s because they're very narrow band circuits and it's not really an issue. So when we have massive amounts of bandwidth to cover, then we actually worry about this as well. So, so impedance matching uses a network to transform an impedance to a desired impedance level over some specific bands of frequency. This is extremely important. Over some specific bands of frequencies, right? Matching networks are effectively filters that absorb the reactance in one of the ports. And the reason why absorbing is why we actually talk about the conjugate matching. Because if you actually conjugate match, make it look like the negative of the reactance, that would actually cancel out. It will become all and then so effectively that's what we're trying to achieve here, right? So we're trying to absorb the reactance of one of the ports. Impedance matching limitations is a trade-off between gain and bandwidth. And the gain and the wider the bandwidth, the less power you have to for the greater impedance match. And at the ultimate limit, you have what's known as span of limitation. And a perfect match, this is extremely important. A perfect match can only be achieved at one single frequency. Right? The rest of it is a trade-off. So that's why when we define impedances, we don't actually, and this is this is true for many of you that are actually trying to do impedance. This is a Smith chart, which is a visualization tool that allows us to see reactances and impedances or conductances and susceptances, depending on how you look at it. But we're looking at the Z circles in here. So perfect matching typically is achieved by trying to get as close to the center of the Smith chart as we possibly can. Right? But we don't normally specify a single point. We actually specify an area. And that area, which is basically a circle, can actually can define the return loss, let's say 10 dB, or the gamma 0.316, or the VSWR of 2 to 1. All the same thing. So if I have 50 ohms, a VSWR of 2 to 1 means that the impedance can be twice as large or half of it. So any impedance between 25 ohms and 100 ohms will satisfy the 2 to 1 VSWR. Okay, easy stuff. That's easy. Return loss, well, actually, return loss of 10 dB is effectively 10 log of 0.316. That's what 10 dB comes from. And the 0.316 really comes about, is basically the reflection coefficient, is that if you know the actual diameter of that circle is actually equal to 1, right? What section of this represents 10 dB? And is actually equal to 0.316 of the normalized diameter of the Smith chart. That's what it all comes about. So we always give you a parameter, a performance indicator that does that, right? And where did I leave Fanon's limitation? Oh, maybe we'll talk about it in a second. So when we talk about broadband amplifiers, one of the things that we worry about is if I basically let the circuit, if I let the effect of reactances get out of hand, it is impossible to be able to maintain the bandwidth requirements that you need for the circuit. So circuits are reactive. There's nothing we can do, but we tend to water down or decrease its effect. So the same as what I was showing you here. If I have a reactive circuit here, if I have a reactive circuit on RS plus XS, I actually make the RS larger. Right? What do I do to the Q? So if you have a large reactance, right? So you got 50 ohms looking at here, and then you have a high impedance. This is just the base of it. At this worst case, the base is just represented by the R pi and the C pi, right? And the C pi will dominate. So it's a very high impedance. So you have low impedance to high impedance. And then on this side, you have very high impedance. So how do you compensate for that? Bring down that low impedance. Low impedance, very low impedance. And then you basically amplify with another high impedance. And then you basically add another low impedance. So it's a combination of high impedance, low impedance, high impedance, low impedance.
But in terms of units, you always have lower field.
So an emitter follower, which is effectively, oh yeah, right here. So you have an emitter follower followed by a transadmittance, which is this one here, followed by a transimpedance. Right? And then you do another emitter follower, a transadmittance, and a transimpedance. Okay. But the problem with each one of the cells, so what is an emitter follower? Emitter follower, as you said, is the same as a common collector, right? So you're basically just AC shorting a collector, and you have basically a emitter follower. And then after the emitter follower, you now have a feedback amplifier, which is effectively a transadmittance, and then you have a transimpedance section on the next section as well. So you have a transadmittance, transimpedance, and you have an emitter follower. And the transimpedance basically converts current. So if I have current going here, I in, I convert it back to the out. And then the emitter follower just follows, right? So you have a common collector in and you have out. And then you have the transadmittance added at the end, which is this one here. Okay. So how does that look in terms of circuits? Here's an example of an emitter follower. So you have a transadmittance, a transimpedance, and a follower. So the TAS is here. Then you have the TIS, then you have the emitter follower, and you basically cascade multiple. Now the problem is when you're doing this type of circuits, it is very difficult to control gain and bandwidth separately. Yes.
The purpose of this circuit.
Okay, so that's a very good question. Where we use this? So let me give you an example. I'll do it right here. So let's say you have a photodiode, and that photodiode is receiving optical power, and the optical power of the photodiode ranges. It has a dynamic range, right? But on its worst case, what is the worst case for a receiver? Is when you have the lowest possible noise to amplify, right? So let's say this system has a sensitivity of let's say negative 30 dBm, which is equivalent to a microamp, because the photodiode has even though one is in decibels and another photodiode because of the nonlinear characteristics, basically the equivalent of dBms in power, optical power in, are actually converted linearly into actual microamps of current that flow through the photodiode. But you're asking me, where do we use this? Well, okay, so that's basically what's coming out of the fiber, and the fiber is hitting it with a power that can be as low as minus 30 dBm. And this is actually using something called ONU, or an optical network. Not an ONU, sorry, is into something called a PON, which is a passive optical network. And it's effectively a transmitter that goes into multiple receivers down into the metro area, and you're basically getting one of them. And you don't know if you're going to get plus 20 or minus 30. The losses are all over the place. But you got plus 30 dBm coming in, worst case. But this has to go into a PC or some kind of a signal processing unit, right? So on the other side, you have the microprocessor, we're going to call it. But microprocessors are actually based on standards. And some standards could use TTL power levels, whatever that standard is, right? So typically those standards are actually plus minus 1 volt, or at least 1 volt of a healthy signal, so I can actually convert it properly. You got a very weak current, or you have to deliver 1 volt. How do you go from 1 microamp to 1 volt? What is the difference in terms of dynamic range, first of all? 1 million, right? And what is 1 million in terms of 20 log? Because this is current to voltage. We're not really dealing with power, right? So what is 20 log of 1 million equal to what? 120, right? So it's 120 dBs. So you need 120 decibels of transimpedance. Okay. All right. So then you're asking me, what do we do with this? Well, the first thing we have to do is we have to sense it. And the first block is really critical. So we actually use a transimpedance amplifier to give us probably about 40 dBs of transimpedance. dB ohms. Okay, so that means that you have 1 microamp, 40 dBs is equal to what? 100, right? So I have 100 microvolts on the other side. Okay, what do I do next? Keep amplifying the heck out of it. That's what you were asking me, right? So the next thing then it will be to add another amplifier, which would probably add 20 dBs. So now I'm up to what? I'm up to 1 millivolts. I'll explain what the second one is. But this is some kind of an amplifier, right? And then it goes into another one that has 20 dB. And that brings me again to 100 times. So that's 100 millivolts. And then the last one, 20 dB and 100 millivolts becomes 1 volt. So I needed 4 stages of amplification. The first one is very critical because the first one gives me the biggest kick. You had 4 dBs of transimpedance. After that, it basically became voltage. The first one is transimpedance gain. The second one is voltage, right? Once I converted from total current or current to the diode into a voltage, then I just kept on amplifying until I reached the value that I need. It's defined on the other side, right? And we'll talk about those standards in a second. What does that amplifier look like in the middle? Well, it probably look something like this one. And what this is a voltage in, voltage out, called a Cherry-Hooper amplifier. And we're not going to get into the transfer function, at least I hope not. But what it really does is that effectively decouples bandwidth from gain. I can keep on increasing the gain without suffering the bandwidth. And anyone can see there. So I'm going to throw up there. Bandwidth is defined by what? So gain bandwidth, right? So on the worst case, when you have a gain of 1, what is the bandwidth? FT, right? So remember, gain times bandwidth will basically be limited by this curve. At the worst case, when you actually have a gain of 1, then this maximum bandwidth of operation is what we call FT or FT point. And the FT can be approximated, I'll do it again, as GM over 2 pi CGS. And I said it's a constant because I can make the device larger, which will give me larger transconductance, but it will also increase its capacitance. So overall, you're never going to win. Or will I? So this is a very efficient circuit.
This is the voltage.
Yeah. So let's look at 1/2 here. And I'm not really care about circuit analysis, but I just want you to look at this just for a second. Let's look at 1/2 because the other half is just basically the polarity, right? So we got now M1 and M3. So the signal comes through VN1, then it shows up at the input of M3, and then it shows up at the output. So it goes through 2 stages, GMR, GMR, right? So you have, sorry, on the other side here. Yeah. So you have GMR, and then you also have GMR. So actually increase the effective transconductance, right? Okay, so that's really good. So the transconductance has gone up. What about the denominator? That's the question for you guys. Really cool thing they've done. This is actually called an FT doubler if the devices are the same. So we can all clearly see that we have improved the transconductance. But the problem with a standard device is that if I increase the size, I also increase its periphery, I also increase its input capacitance. I give you a huge hint here, input capacitance. What are we doing there? We can get more current, i.e. more transconductance flowing to RF and R2, but the input periphery has remained the same. So guess what? If M1 and M2 and the GMR product of those two is the same, I effectively have double FT. You guys see? And okay, so that's one really cool thing about Cherry Hoopers. Secondly, they're very stable. By the way, if you do if you get a really flat response across bandwidth, they have massive bandwidth improvement because of the FT doubling effect. But secondly, you now have IS1 and IS2. And with IS1, I can do what? So how can I take advantage of IS1 and IS2? Well, there's two. So IS1 allows me to control the bandwidth, right? This is really going to affect the input capacity. IS2, I can independently, I can keep the bandwidth the same. So the Cin stays the same, but I can actually increase the gain. So I have independent control of gain and bandwidth. Wait a minute, what happened with all this gain bandwidth product that you've been talking about? So this circuit violates that, right? And it helps you in many ways. So Cherry Hooper amplifiers are a workhorse of any optical communication system. And no matter where you go, if you go to CNL or Marvell or Nokia, anytime you need to go and do something like what I drew here, you're gonna basically see these reproduced everywhere. Current to voltage, transitors, followed by Cherry Hoopers. Right? So that's it, right? So
Question, let's say you have this circuit, like this circuit is done for worst case scenario, that you get a very small signal. Right? So let's say you actually do get like a proper signal. You only need to amplify that much.
No, but the problem is this is okay. So you have, remember how I said, well, I used this in the wrong context, but if you have a high-speed chip, right? The core of it is CMOS. Then the next layer is actually called CML. And then the next layer is really the analog part. So what I've done here, this section that I showed you left, that's the analog part. Then we actually have to get in, let me remove that. That's not microprocessor, that's incorrect. This here is actually the CML. Oops, weird, CML. So now we're passing it from analog to CML, and then CML is going to pass it to CMOS. So CML, by definition, requires a minimum voltage. It's a standard. And that voltage is 1 volt. 1,000 millivolts to be exact. Right? So, and it can be as low as 250 millivolts, and it can be as high as 1.2 volts, but in reality, it's only about a volt. And I'm using the volt because it was easier to calculate here. So that's the problem. The problem is to comply with standard chipsets, you have to deliver CML voltage level or CML amplitude level. And that's where you need to amplify the algorithms. Now, of course, this thing is not very easy to do because 120 dBs of gain amplifier, what could go wrong? Okay, that's like taking a stick of dynamite and just going and barbecuing, you know, and see what happens, right? Hopefully, you're not gonna. So it's a very unstable like circuit. There's a lot of things that could go wrong with it. I have 3 PhDs in myself that have actually spent a good part of 7 years trying to solve a physics problem, which is the one I just described there. That minus 30 dBm didn't come from nowhere. So we actually did it. And we published in that journal that I told you, that is famous one from San Francisco. So we actually just published on December of 2024, after 7 years or so. So it was pretty rewarding that we were able to do what no one else has done with this type of amplifiers. Okay, so where are we? So we talked about gain bandwidth limitations. I said that the matching network can achieve its ultimate goal of performing perfect impedance. What does perfect impedance matching mean? So if I go back to the Smith chart, what does perfect impedance matching means? You're hitting the center of the Smith chart, right? Perfectly. Anything else will be a trade-off. Will have to be within a boundary, within whatever parameters you're given. What is the return loss at the center of the Smith chart? Right at the center. Infinite, right? And if you're doing your return loss, whatever, you get something that does this, right? Very low, so it's very sharp. So, but is this good for a broadband circuit? No. What we want is we actually want something that does this. So maybe not as high, but it basically does something like this. So notice how the level went up. And if the level goes up, it means that I'm not in the center. I'm somewhere in the middle here. I'm going to use a different color. I'm starting to get in trouble here. I should really be using blue. I already have red. That means that I'm probably not going to, I'm doing something like this. I'm never in the center, but I am within the boundary. So what I need to do, right? That's the trade-off. You now have traded perfect matching for larger bandwidth. And what Fanos tells us is that this is not black magic. It really has to follow. Oops. Did I cancel something here? What did I do? Oh, here. Okay. Very dangerous to have editing on this thing. Okay. So what it's telling me is that there's actually not, this is not black magic. What it is really that the limits on the maximum return loss you can get, or the maximum gamma that you can get, is actually defined by this function here, which is Q2 minus pi of Q2 over Q1, where Q2 is the desired bandwidth, and Q1 is how much reactance you actually have to deal with. So the larger the reactance, the larger the Q1, the lower the gamma. It's going to be a problem, right? So effectively, what we got to do here is we have to be able to either reduce the reactance or deal with the actual requirements that we have for banking, right? It's a very powerful thing, and you're often see it and just bypass it without really understanding the principles. And we're not really going to get into this as much, but just to tell you that I was looking again into a visualization tool like a Smith chart. What it also tells me is that I can not only plot impedance levels, but I can also plot Q circles. And those Q circles are directly proportional to Q1. So if I can control Q1, I can then, for a given bandwidth, be able to improve the matching. And here, the farther away you get from the center, the higher the Q, and the higher the Q, the lower the expectations are on the matching, right? So with these Q circles, we can go ahead and basically plan what the expected bandwidth are. But question is, if I have to go from point A to point B, you can see that depending on the that you have defined or the maximum Q that you are allowed, you're actually limited to within the circle. So when you're doing impedance matching, each one of those will be a component, right? So if you had, if you had a termination, which is here, so this is basically your RL or X load, whatever that is, and then you got a source, the matching element in here, so I've done 1, 2, 3, 4, 5, 6, 7, 8. So that's effectively 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 elements, right? And one does a series L, and the other one actually does, again, the parallel C. So you go LS, CP, LS, CP, LS, CP, right? LS, CP, LS, CP, and you can go from there, right? It's a very complicated multi-component matching to be able to do this, but it can be done. And with that, in the Q2, and so in the Q1 value that I'm maintaining, that would actually ensure that I now can match over a bandwidth, a larger bandwidth Q2. Because to maintain the same gamma, the Q1 halves, Q2 doubles, right? Just three factors. It's the ratio of Q2 over Q1. So if I reduce the Q by a factor of 2, if I reduce the Q1 by a factor of 2, my Q2 can be twice as big. And Q2 is omega over omega B minus omega A, right? All right, so gain bandwidth trade-off, we talk a little bit about that. We can trade gain with bandwidth by using resistance feedbacks. And one of those is either a Gilbert cell, so here, so you have your RS, that's your series feedback component. And really what it does is that when you have a feedback amplifier, you basically, when you typically see the transfer function of an amplifier is like this, right? It's decaying. So you got gain, and then you have the FT, and so on. But what you end up doing when you actually use a feedback is that you effectively, let me see, where's my red here? You're effectively trading gain for bank, right? So you can, so you basically, where you have too much gain, equalize it, and then a high gains basically gives you a different kick effect so as to actually optimize the bandwidth. So you can do it with a standard differential pair, or you can use it with a Gilbert cell. You guys know what a Gilbert cell is? Ever heard of it? Gilbert cells are effectively using something called a mixer, and what it does is it is effectively an equal differential pair by having an upper quad, switching quad, that actually allows us to amplify or multiply signals in time and basically translate them to frequency. And we can use similar effects to be able to improve the gain and bandwidth. And ultimately, we have this Kerr-Hoover, which is what we talked about before. You get twice the transconductance with the same input capacitance, and then you can alternatively control both the bandwidth and the gain separately, as you see here. Okay. Then, okay, so we're done with the gain bandwidth trade-off. So you can train gain. Did you have a question? Okay. So shunt resistive feedback, series resistive feedback, Gilbert cell gain, trade speed for high gain, and Kerr-Hoover trade gain for high bandwidth. Right. So those are the sort of competing blocks that we have here, and we don't have that many. This if you look into your fourth year project, or if you go to Marvell and look at the state of the art, you're going to see a Kerr-Hoover in both. So there's not a lot that we have to work with. Yes.
The Kerr-Hoover is setting up like these IS that you can use to tune the gain and bandwidth. There's always a trade-off in there too, like if you're going to increase the gain.
Yeah. So the question is, okay. So why do I need to have gain bandwidth control? Isn't the goal to always have the highest gain and the highest bandwidth? Not necessarily. Okay. And the reason for that is that if you have, okay, so that's an excellent question. I don't even know if the right space to do it is here. So let me see. Oops, eraser. Let me see if I can maybe move it back so that we can. Wait, coming back to one black. There we go. Where can we do that? Okay, maybe here. So gain high, bandwidth high, always. Okay, so if you look at an amplifier, it's going to do the transimpedance amplifier as an example, right? But it's the same as the Cherry Hooper. So, and then typically you have a diode, right? So you will have a diode in here. And that diode, for all effective purposes, can be modeled as a capacitor, right? So then what happens is that if you look at the noise, right, the noise that you have at the output can be input referred, right? And typically noise, what you do is you basically look at the noise level, but you integrate over a bandwidth. And that bandwidth of integration becomes the amplifier. So if the amplifier effectively is super broad, guess what? We're getting the signal level, but we're passing all the bandwidth that we can. Right? So what we actually need to do is we need to do filtering. So we need bandwidth, but just enough bandwidth. And in fact, the lowest possible amount of bandwidth that I possibly can get away with. So now I'm getting even complicated. I said I needed all the bandwidth I can. I need to have the possibility of having all the bandwidth that I can. But then there's other factors like, for example, noise shaping, where you actually need to attenuate the noise contribution so that you're only passing the noise that you absolutely have to. Because that limits, if that is input referred, that would actually limit the ability to sense small signals.
So you're saying, for instance, if we can put this on it, that means we kind of limit the amount of noise per second.
Yeah.
So the whole point is that, so the whole point is to minimize the noise.
But what does the Cherry Hooper do? I can play around with the bandwidth that I need, but I don't have to touch the gain. The gain is the same. So it's independent gain and bandwidth control.
Sure, but then you can't, like, using the Cherry Hooper, you can still have like a really high gain, really high bandwidth if you wanted to.
If you want.
Okay.
Yeah. But maybe I don't want both, right? And the problem with the standard amplifier section is that if I change the bandwidth, I change the gain. If I change the gain, I change the bandwidth. And that is not to my advantage. So that's why the Cherry Hooper is so powerful and so widely used in this type of circuits. Okay. All right. So the next one is this one. You have a low-pass filter. It's actually this curve shown here. Maybe I should use colors. Let's start with green. Okay. So this curve here in green is effectively the channel. Right? So you got a channel here, and I'm just going to put it in black here, but you got a channel. Or just don't even bother about the channel. It's just the actual transfer function of the circuit itself, right? So you got a first or second order, whatever that is. I'm not really gonna get into orders, but you got a roll off. You got a pole frequency, right? So this circuit, if I was to plot the gain as a function of frequency without any inductance, you will see that the R and the C will actually form a pole. And that pole frequency, if you can measure the 3 dB point, or the point on which the voltage drops by 3 dB, which in voltage is equal to what? What's 3 dB in voltage? What's 3 dB in power and what's 3 dB in voltage? Root 2, yes. No, 1 over root 2, right? So 1 over root 2 is in voltage, and 1/2, because it's 1 over root 2 squared, is in power. So you either get 1/2 of the power if it's 3 dB power, or you get 1 over root 2 voltage if it's in voltage. But here we're dealing mostly with voltage, V in and V out. So for the green curve, you can define the 3 dB gain, voltage gain, right, by the actual point in which the pole basically just kicks in. And I've done that curve on green, and you have the point in which the 3 dB point occurs. So we're going to call these F1. Okay, but you can actually introduce a peaking component, L. And that peaking component, it actually has the effect of doing what you see here. This curve, and just going to use purple. Try to avoid green and red. So there you go. So this one here, basically you have an L for peaking. And based on what value of L you do, you can control the amount of peaking. But regardless of what I do, notice that I've actually pushed the actual frequency point by a factor, right? So, and this factor, because what I'm actually doing here is not plotting frequency, I'm likely plotting the log of frequency. So that improvement is massive, even though it looks like a tiny little bit at the end here. Just think about it. We're actually improving it by a factor of 1.7x. It's a lot of frequency, right? 1.7x. That means that if I have 100 gigahertz of bandwidth in an amplifier, inductive peaking can get me to 170. That's massive. The same process. I don't have to go and pay more money. I don't have to get anything faster just by adding an inductor. Yeah, crazy. Now, this also can come back and bite us as well, because so if the curve in the purple gave us the maximum bandwidth, so we're going to do F2 for the one in the middle that I haven't talked about, and we're going to do F3 for the one in the purple, right? So if the ultimate goal is to get the largest amount of bandwidth that it possibly can, I should stop at some really huge value of inductance, and I have something in the middle called L off. Why do I care about L off? Isn't the purpose to have bandwidth? We want peaking, but not too much peaking. Why? It starts. It will resonate for sure, but it's not the main reason in an optical system. Based on what you know now, based on what was the first few lectures that here have been. So we want gain, but we also want something, especially with broadband signal, right? So remember, you have a very large spectrum of data that you're trying to pass.
You're not evenly amplifying your signal passband anymore.
So the actual different parts of the spectrums is a different gain, and obviously a different phase, which you have in the plotting here. And as a result of those two, you're also going to have group delay variations. And those group delay variations are going to come back and close the eye. So you're improving it in bandwidth, really messy, right? But the gain peaking is so much that when you superimpose a million eyes on top of each other, because of the different effects, you're going to see that the eye closes. So what's the purpose of all that, right? So you do need to peak it, but you need to peak it just about enough, which is the value of L off. Yes. So group delay, by definition. So if you look at, I should actually just, so group delay in a nutshell is delta F over, oh, let me see, delta phase over F as well. So, but there's a 2 pi factor in there, so I'll just grab the oops. Jeez. Delay. Okay, so let me just grab these and I'll put it on the notes. So screen rate. Save it. Then we go to good notes. And I probably can't put it. I'll just add a new slide here so you guys can have it because it will help you for the assignment. So we are on this one and I'll add another one after. And we'll introduce an image. And there it is. Done. Not an image. Okay, so if I was to actually, oops, sorry. Now it frozen me. Okay, so we're gonna go back and reopen it. That's the danger of doing things in real time with this program. Here. Okay, there we go. So if I was to actually plot phase as a function of frequency, what you want in reality is to have the dash curve, right? To have a basically constant phase as a function of frequency. So the frequency goes up and the phase in the phase exactly remains constant, or the slope. The moment that that becomes a variable, as you see here, then you now have different phases affecting different parts of the spectrum. In those phases, what they actually do is they end up adding constructively and destructively, and more so destructively when you're actually trying to analyze cascaded systems. So if you're in the business of doing filters, or if you're in the business of doing multiple gain stages, like the one I show you, the transimpedance followed by 5 stages of amplification, having different group delays cascaded and amplified one on top of the other is a recipe for disaster. So you want everything to be as flat as possible, right? And that's also almost never possible as well. If I was to actually plot the group delay, so if I was to, if I was to look at a transfer function that does this with picking, and I was to plot the group delay will look like this. Okay. And now the problem is, if you then take the 3 dB point as being here, look what's happened to the group delay. And this is just gain. Right? It's really in conflicting between the amount of group delay, and of course you have deltas of group delay that you're allowed to that you're permitted to work with. So yeah, you get more bandwidth, get more group delay, and you cannot really deal with that much on the high end as well. And then the other problem is, I also have a problem where I can't really make use of the full bandwidth, because now, so the answer to this problem would be, well, if you have that group delay shooting up towards the high end, wouldn't it make sense then just to make this as large as possible? Wouldn't that solve it? That means that we've actually bypassed the problem, and it now becomes a problem for later that I really don't have to deal with. How can you do that? I explained 15 minutes ago that you couldn't, because there's another secondary effect that we have to deal with. Why can I not do just extend it so that within the bandwidth of interest, which is this dot here, I have now flattened the group delay and flattened the gain. So if I extend the bandwidth, I can flatten the group delay. If this is basically the bandwidth of interest here, I have flattened the group delay, and I've flattened the gain. The peaking happens later, and this tuning of the group delay happens later. But what is the problem? That the actual gain transfer function is also serving a third purpose, which is noise cancellation. So if I open up the bandwidth, I'm passing more noise. And that noise will show at the output, but can also always be input refer. And it would actually now start to limit the minimum detectable noise that you actually can work with, which is your thermal noise level in your system, right? So you can see how complicated this thing is. Group delay, which again affects intersymbol interference, and it closes the eye. Then you have noise, which also limits how much more you can detect the signal. It basically makes the one is jitter, and the other one basically affects the the thickness of the eye on the bottom and top of it, which actually closes it as well. And then you have group delay variations. You have group delay variations. You have gain peaking, and all sorts of stuff happening at the same time. Is that clear?
Group delay, does it affect the diagram? Does it affect the axis?
Exactly. Yeah. Yeah. Well, it's difficult to say just the x-axis, because, as I said, as the eye becomes crunched. So you got amplitude, and then it's almost like I always make analogies. So I always tell my son plays soccer, right? And sometimes we take him down to the U.S. and he plays with the best of the best, and he realizes that he's not as good as he is in Ottawa or he's in Toronto. And I say, well, the difference is when you take time and space away from what you're used to do, then basically you got a different situation, right? If we were given infinite amount of time and infinite amount of space, we could all solve any problem that we're given. It's when you're faced with it in a very short period of time, right? And you have a very small, limited series of tools that you have to work with. So back to your question is, you have the amplitude, but you also have the eye width. So as the frequency increases, this eye width becomes smaller, right? This is the opposite. So back to your question is, if it's thick from a thermal point of view, that thickness not only affects you vertically, but it also begins to affect you horizontally. So what I'm getting at, right? So now you got a combination of both. Does that make sense? Right? Now, if you have a signal that does this, oops, that's supposed to be straight, then I could say that whatever happens here really doesn't really affect it. We can ignore it. In fact, one of the tools that we use in the lab to try to, because we got noise coming from two sources. One is thermal noise, which we know now where it comes from, right? All this noise shaping and everything from every noise source in the amplifier being referred back to the input. And then we have what's called transient noise. And this transient noise is peaking and all this other stuff, right? So and then you have them all coupled together. So what you get at the end is you basically get a reading for SNR, a reading for a bit error. So how do you decouple one from the other? One of the ways to do it is to reduce the speed by a factor of half. Because if you reduce the speed, again, you're giving the soccer player either more time or more space, and then you can basically see a little more out of it, right? So you decouple things by doing that. You could also give twice the amplitude. So you can give twice the amplitude, half the frequency, so you have twice the time. And then now giving more space and time. And decouple one from the other. So we do tricks like that when we're actually measuring optical systems. Okay, so back in here. So L opt is good, but it cannot be too much, right? So there has to be a specific value. And that specific value, I don't know if I show you here. Here's an example of the magnitude of 0.7, which is 1/√2 approximately, right? And then you see the normalized frequency, so it's normalized. Okay, so you see the 3 dB for the standard one, and then you see the actual bandwidth going as high as 1.8, 1.9 million. Right? And now you look at the phase. See the phase with no peaking. So you see some phase variation. You see the phase with maximally flat and maximum bandwidth. Peaking all over. You want this to be a straight line, but the optimal group delay is actually that straight line, flat curve that you see. Okay, and we're not going to get into this because I think it's beyond the scope of the course, but I think it's good to know because you're probably going to hear this term sometime in your professional life. But this also has to do with filtering the shape of the filter that you're trying to use, which is defined by the values of L's and C's. So far in your 3.5 years of electrical engineering, what type of filters have you heard about? We don't have a course in filters, but you must have heard about filters, right? So you can have maximally flat amplitude. Which one is maximally flat amplitude? Butterworth, yeah, right. And then you can have a sort of a Chebyshev as well, which is kind of a ripple effect on it, but you can improve the selectivity. The problem with maximally flat amplitude is that it doesn't have a lower selectivity. Maximally flat amplitude, the selectivity is not so good. So if you want to actually swing it around and make it do a sharp turn at the end, then you do something like a Chebyshev. But neither one of those is good for maximally flat group delay. there's something out there called a Bessel-Thomson function or Bessel-Thomson filter. So when you're in a filtering system or using equipment at Siena, at some point someone's going to say we're going to use a fourth order Bessel function filter to be able to help us with group delay. And now you're going to say, wait, that's that weird filter section that allows us to have maximally flat group delay. So the purpose of a transit. So if I go back to the where is it? If I go back to the cascaded amplifier that I did for you guys here, right here. So this one has a Butterworth control, right? So ideally, if I wouldn't even need any equalization. If I was to find a magical way to actually put a Bessel-Thomson function in each one of those four, no equalization needed. I'll be good. Well, the channel still has its own thing, but you can do a channel equalization and all the other stuff. But so you have the group delay issues to deal with the channel, and then you have the group delay and all this other stuff happening with the electronics inside the channel. But so I have a PhD student, actually, Alexander. His thesis is to actually come up with a magical Bessel-Thomson transfer function, and how can he synthesize it with respect to RLCs in terms of that transimpedance amplifier. That's his PhD thesis. And it's been at it for 4.5 years now, or 3.5 years. And he's getting there. So he has a synthesis way of actually being able to find a magical Bessel-Thomson function, right? Okay, so let me see. I don't want to leave without giving you at least some hint on this. I thought I had a. Okay, for the analysis of this, so if you have an RLC, ignore the translation of the device. We're basically asking as a transconductor, V out over V in, and for all purposes, if you remove the output resistance and the output capacitance, this becomes high impedance, right? GNR. So for all purposes, if I was to actually look at the actual impedance of this node here, I would actually end up with something that looks like this. I have an input current, and that input current branch out into two. So you have the current going to the capacitor, and you have the current going to the inductor, right? And you know that the transfer function, or V out divided by I is equal to effective impedance of that, and we can then go back and simple calculation of it. Okay. Now, here's the deal. So that gives me an input impedance of Z as a function of omega of R plus J omega L over 1 plus J omega RC minus omega square LC, right? Second order. But if we were to introduce parameters L equal M R squared C, and the highest frequency or the bandwidth improvement as 1 over RC, plug it back in there and show that M can actually be controlled as a function of L. That's really what it is. So I'll let you sit with that for a little while and then see if that helps. The L optimal is actually shown here. So 0.4 times R squared times C. That's the optimum value of L. So prove it. Put an M equal to that number and then see if that actually helps. Okay, so that's the assignment. One of the questions for assignment 2. What else do we have? How does inductive peaking extend the bandwidth? In the frequency domain, you have, that's easy for us to see. Frequency domain is not a problem. We see that there is a kind of a kick in the transfer function, and when the bandwidth starts to decay, I actually have the opposite effect with peaking, right? It's almost like a channel inversion. It's always about the channel inversion. So the green curve is starting to decay, right, with a negative slope, and then the L naught goes up by equal magnitude, properly designed. It kind of cancels out that effect, and we have an extension of the bandwidth. Easy to see that, no problem. In the time domain, what do we have? So gain peaking a high frequency. In the time domain, is basically energy stored in the inductor and it's basically used to delay the current to the resistor, right? So the low value temporarily increases. So that's effectively what we're doing. We're using impedance transformation as well. There's other ways to actually do inductive peaking. The interesting thing is, as useful as this is to help you with bandwidth, one of the biggest problems in circuit is trying to control peaking. And often I don't even need to have peaking. It just happens, right? Because every time, so that L, even though it's showing us an inductor, it could just be the trace that goes to that node, just a little piece of metal. And that little piece of metal has that effect, right? So that's a problem. The other one is the use of, so you can have series chunks, or you can have peak. So you can have double series peaking, as shown here. So you have L1, L2, and L3, or you can actually use something called a transformer, and that's a series, right? So you have two coils, and they're basically exchanging magnetic energy through a coupling factor, and that is a transformer. And that actually uses, you can use something called a T-coil. That's actually very famous. If you go and design high-speed circuit, you're probably going to start not with this, but always with a T-coil. And the reason for that is that the T-coil allows you to make use of two inductors and a capacitor. And this capacitor is something that you have there anyway. So you're basically making use of a parasitic that is there, either through ESD or a pad capacitance or whatever. And you're introducing an inductor, but what really is doing is controlling the reactance. The reactance of that LNR is hard to control, but the reactance of an LCL resembles what? What resembles a series L, shunt C, series L, shunt C, series L? A lossless transmission line. There you go. Okay, I'll leave it right there. You think you guys have enough? Next week, I will be here on Tuesday, but I won't be here on Thursday. So what I'm going to do, I don't think it's good to bring Alexander to recite the course notes that I have anyway. I will prepare a recorded lecture and you guys can see it, okay?
Next Thursday?
Yeah, that's the 13th. I will make a note on, oops.
Post the week 1 slides. Week 2 slides.
Yeah, there's week 0. So I've given you these two. Week 0 to week 2. They're not on Brightspace.
Oh, they're on Teams?
They're on Teams. So look on their files. Yeah.